Hello, I'm Vinícius Duarte. Today I'll be talking about integrated modeling of fast ion relaxation in tokamaks using a two-dimensional quasi-linear approach. This work was done together with Nikolai Gorilenkov, Mario Podesta, Roscoe White, Herb Burke, and Jeff Letts. And this work has been mostly funded by the ongoing SciDec project on integrated simulation of energetic particles in burning plasmas. So that's the outline of my presentation. I'll try to make the case for modeling fast ion transport using a reduced approach such as quasi-linear theory. And then I'll move on to showing a self-consistent formulation of quasi-linear theory for discrete modes, which is the case of Alfvénic waves that interact with fast ions. And this is a recent formulation we developed. Then I'll show verification and validation of such formulation, and then the development of the resonance broadened quasi-linear code, the RBQ code, and its integration into TRANSP, and then finally the summary and outlook. Okay, so not everyone is familiar with what quasi-linear theory is, so I thought of showing an introductory slide on the basics of what quasi-linear represents. So in this presentation, I'll be using canonical variables, which are the constants of the unperturbed motion, the energy, p phi and mu, so kinetic energy, toroidal canonical momentum, and the magnetic moment as the coordinates for the interaction, the resonant interaction between particles and waves. So in a tokamak, it's convenient to use such formulation in terms of the actions to exploit the symmetries. So in an ordinary kinetic formulation, we have a distribution function, which is a function of angle, actions, and time. So this omega here is written in terms of the actions. J is a combination of the actions, and this is Hamilton's equation. So the distribution function is a function of angles, their canonically conjugated actions, and time. So in a bump on tail framework, that would be position, velocity, and time. And that's the kinetic equation down here, which is Vlasov equation in the absence of collisions. Omega bounce represents the bounce or trapping frequency, which is proportional to square root of mode amplitude. And so that's the ordinary kinetic theory. And quasi-linear theory essentially looks at a coarse-grained distribution function. So basically, the distribution function is now an average over the angle phi here. Or in a bump on tail case, it would be the average over position. So the whole kinetic equation reduces to a diffusion equation. And instead of being three-dimensional, now it's, before it was six-dimensional, now it's three-dimensional, so much cheaper to simulate. So that's, quasi-linear theory is valid when the eigenstructure and the resonance condition do not change appreciably in time. And it's one of those examples that were independently developed by the Soviets and the Americans in the early 60s by those two references, and later generalized to action and angle variables that I'll be using in this presentation. So historically, the Cherenkov criterion has been invoked to justify the applicability of quasi-linear theory. So again, this represents the resonance in action space. This is the angle. So you have, in this case, two resonances, two chains of resonances in phase space. The Cherenkov criterion is when the amplitudes, here represented by the bounce frequency, of the two waves is large enough that the separation between them is less than the width, the sum of the widths of the resonances. So in that case, the particles do not belong to a particular wave, but rather they're shared between waves, and that introduces chaos, and collisions might introduce stochasticity that can be used to justify the use of a reduced approach when you do not need to track the whole bounce motion of particles. Then quasi-linear theory is a good theory to represent what happens in the dynamics of resonant particles. What I'll be showing in the first part of this presentation is that we developed a new self-consistent quasi-linear theory near marginal stability, and that has two very interesting properties. First is that it automatically recovers the saturation level predicted by nonlinear theory, and also I'll show that the diffusion coefficient and the resonance function that appears there can be naturally calculated analytically. So before getting to the numerical work, let me show an experimental example that suggests that quasi-linear theory can also be a good theory to represent the governing dynamics of energetic particles in resonance with Alfvén waves. So this is an example of the so-called critical gradient experiments in D3D. And they had very interesting observations that what is plotted here in the left is the fast ion d-alpha diagnostics that infers the density of fast ions versus minor radius for several beam powers. And what is interesting is that as the power is increased, the density builds up gradually, but then there is a threshold above which you keep injecting more power, but you don't get a taller profile for the density. And together with that, we can look at the solid state neutral particle analyzer that interrogates a specific region in phase space. But what is interesting here is that the flux of energetic particles is basically zero below a certain threshold in the beam power. And above that, you start measuring appreciable transport of fast ions. So that is suggestive that the transport in this case is regulated by the overlapping of resonances that should be happening at this beam power here, at this particular region of phase space. So this stiff transport is suggestive that quasi-linear theory should be good for this case. And quasi-linear theory is much cheaper than the whole nonlinear theory, so it leads to quite fast simulations compared to the whole nonlinear case. Okay, so let me show you the formulation we recently developed for quasi-linear theory. So historically, quasi-linear theory used a heuristic broadening function. So in this pioneering paper here by Burke, Brasman, and co-authors, they had a very interesting formulation of quasi-linear theory in which here what is shown is basically the same phase space plot in action variables, but here is time instead, in which you have seven resonances that evolve in time. Their widths are represented here. And in this case, in the left, they do not overlap, while on the right, they do overlap. And when they start overlapping, they release more and more energy, which leads to more and more overlap. So this paper was the first to propose this resonance broadened quasi-linear model, although using a heuristic broadening function that I'll show later. So the broadening of resonances is something actually very present in many branches of physics, especially in atomic spectra, that you have, for example, not only collisional broadening, but you can have several other types of broadening due to a number of effects, for example, relativistic effects and many other. In plasma physics, the broadening has been considered in the so-called strong turbulence theories, but this is very different from what we look at for Alfvénic waves. So for strong turbulence theory, you have basically a very dense spectrum of resonances overlapping from the outset in a collisionless plasma, but they're not applicable for discrete modes in the presence of collisions. So this is what the set of quasilinear equations look like. So again, I remember that in the first slide, I showed the diffusion equation. Here it's basically the same. It's diffusing in action variables. And in the diffusion coefficient, you have, in the absence of any broadening, you have simply a delta function. But we are going to see that a self-consistent formulation leads to some form of this function that is not a delta, as soon as you consider either collisions or any nonlinear effects. So you broaden the resonances. So that equation for the relaxation of the distribution function is supplemented by an equation for the evolution of the amplitude. So recall that omega bounce, the trapping frequency, is proportional to the square root of mode amplitude. This is the growth rate and the damping rate. And the growth rate is the usual Landau prescription. It's proportional to the local gradient of the distribution function at the resonance. Okay, so the formulation we developed, basically the starting point is kinetic equation, no assumptions here. We have some collisional term that could be, for example, a crook, creation and annihilation term. We can have pitch angle scattering, which is second order in a second order derivative of the distribution, but also we can have turbulence and other terms there. And I'm not showing the analytic development, but in words, I can say that near marginal stability and under some circumstances that are common in tokamaks, we can exercise perturbation theory. And when collisions regulate the dynamics, so basically when collisions are faster than the characteristic growth time of the wave, then but what happens is this kinetic equation it naturally leads to a diffusion equation without any further assumption than those that I already mentioned. Collisions dominating the growth and near marginal stability. So basically we get this equation here that I just showed. Not only we get that, but also we get self-consistently the diffusion coefficient, those resonance functions, which in the case of this crook operator, it's a Lorentzian like this one. For the case of pitch angle scattering, it's this function here, which are shown here in this upper plot. In green is the heuristic broadening that was previously used. And in red and blue are the crook and the pitch angle scattering cases, which are self-consistently calculated. And in the bottom plot is the delta F, the modification of the distribution function around the resonance, which the resonance is at omega equals 0 here. So the center of the resonance is here for all cases. And the theory also, it's local, so we basically have boundary conditions at infinity. But the interesting outcome of this is that we could prove analytically that using those broadening functions here, those resonance functions, what happens is that every time we use them in quasilinear theory, then quasilinear theory exactly replicates essential features of the fully nonlinear theory. For example, the growth rate and the saturation level, they are automatically built into a reduced approach. So the self-consistent formulation allows for a reduced approach to maintain essential properties of the whole nonlinear approach. And Jeff Letts talked about details of this formulation in his poster in this meeting. Okay, so verifications and validation of such model. So the first verification is basically the delta F I showed before, which is the green curve from analytic theory, and the red and the black are guiding center simulations using the orbit code for two different collisionalities. And you see that the fit is for the amplitude is quite reasonable for those cases. And this is a tokamak, a real tokamak geometry. And additional verifications, which give us some confidence that the code is behaving as expected, is that we have three expressions for the saturation level in limiting cases. So the first case is a collisionless case. That's not an analytic expression, but it comes from Vlasov codes. And the two others are collisional cases with damping. One case analytically calculated near marginal stability, the other one far from marginal stability. And in all three cases, the amplitude symbolized by the bounce frequency recovers that expected saturation level for all three cases. All those three limiting cases that we know what should be the saturation level. So again, here I repeat the set of quasilinear equations, the diffusion equation for the distribution, the growth rate expression proportional to the gradient of the distribution, and the equation that steps the mode amplitude. And what I show here in those two plots is a fully nonlinear simulation using this cubic equation derived by Berg, Breisman, and Pecker in '96. So that's a fully nonlinear approach near marginal stability, and that's a complicated equation because not only it's nonlinear, so it's cubic in the mode amplitude here in this last term, but also it involves time delays in the arguments of the amplitude. And not only that, it's an integral differential equation. So the green curve is the simulation of that nonlinear formulation, and black is what the quasilinear theory that we formulated yields. So basically you see that as expected, quasilinear theory being a reduced approach does not capture all the fine details of the evolution of mode amplitude. However, it does capture the essential information, which is not only the time scale for the amplitude to saturate, but also the exact saturation level. Those are further verifications of the code RBQ, the resonance broadened quasilinear code that we've been developed in 2D, so in energy and P phi, while mu is the magnetic moment is approximately conserved. So it uses an implicit alternating direction scheme. And here is the verification for three different cases. So in all three cases, we considered, just to check the numerical scheme, we considered a delta function at the center of the domain. So a distribution which is a delta function injected at a certain point in space and in velocity. So the 1D case is basically what we see here in this left plot, which is the broadening of the delta function to a Gaussian only in one dimension, only in P phi, because we constrained it to do so. If we allow diffusion in both directions, then it becomes an isotropic diffusion. However, we have from Hamiltonian mechanics this constraint that if a particle is interacting with an alpha-n wave, then a combination of P phi and energy is conserved, and that's what we see. So we see this preferential direction for diffusion of energetic particles in a slanted path in energy and P phi. This is another example of the code. So this is the case of a reverse shear alpha in eigenmode. That's the mode structure. And what we compare here is the saturation level in the quasilinear code with a fully nonlinear code using a bump on tail setting called BOT that was developed by Matt Lilly 2010. So across one order of magnitude, we see that it's very similar. As expected, it's not the same, but it's quite similar, and especially this small disagreement here is related to mode structure effects. And the horizontal plot, the horizontal axis is the effective collisionality that the energetic particles feel. So let me mention the integration of the resonance broadened quasilinear code into TRANSP, which is a prototype for whole device modeling. So it's a transport code. So again, this resonance broadened quasilinear code, it's a reduced, but I claim it is still realistic. So we capture the essence of the dynamics. So this is an example of the workflow of the code. In the first step, we use a linear MHD code called NOVA to calculate the eigenstructure using TRANSP as for all the background plasma parameters. The second plot, I showed the resonances. So this is energy versus P phi, and you see several resonances here, several of those lines. And around each resonance, you see a lot of nearly perpendicular cuts here. And those are the broadening around each resonance. So in each position, each point of the resonance, you have a different broadening because you have different collisions there in different mode structure as well. And that is used by post-processing the NOVA code. And then the resonance broadened quasilinear code evolves self-consistently the distribution and the amplitude of the modes. So for this plot here is the amplitude versus time for 7 different collisionalities. And not only it affects the saturation level, but also the oscillations and eventually the intermittency patterns. Those are examples of, well, the first plot is just the spectrogram of the discharge we look at. And in the bottom here is what TRANSP calculates. So basically for the neutron rate, which is a proxy for the losses of fast ions, in black is the classical case. So classical meaning when alpha n waves are not considered. And you see that those ups and downs are because of the beam blips that were used in this particular experiment. What is measured is in red, and what RBQ calculates is in brown here, which is reasonably close to the measurement. And on the plots on the right show the distribution functioning in pitch angle versus energy space when alpha n waves are not considered and when they are considered using RBQ. So you see a significant depletion of the fast ion density in the presence of alpha n waves. So my summary and outlook is that in the first part of the presentation, I showed a new quasilinear theory systematically derived near marginal stability. And the outcome of that work is that the broadening functions that appeared in the diffusion coefficient of the quasilinear equation, the diffusion equation, they emerged spontaneously before we didn't know what they were, and we used the heuristic approach only. That framework allows quasilinear theory to replicate the exact same saturation level as in nonlinear theory, and that formulation has been validated. It is valid for both isolated and overlapping resonances. In an experiment, we never know what to expect, what regime we're in, so it's good that it works in both. Then I showed the development of the resonance broadened quasilinear code, in which those functions were programmed. The code was developed, verified, and validated, and further integrated into TRANSP. So what we realize is that the 1D case in which diffusion is only along P phi, although it does capture some features of the transport observed in experiment, but we need to go to fully 2D in energy and P phi to really make any quantitative prediction or interpretation. And the ongoing applications are, we're trying to explore and understand possible transport channels to hopefully inform some phase space engineering. And there are ongoing applications of the RBQ code to ITER, which was presented in this meeting by Nikolai Gorilenkov. Thank you very much.